Okay, continuing our review, 7.4 graphing. So again, we did several places in the semester where we graph. I'm trying to pull all of those together into one area here. The first time we really saw graphs that we had to do, we had these parent functions, okay? You got to know all 6 of these: x squared, absolute value of x cubed, the cube root of x, or x to the 1/3, the square root of x, and then x to the 2/3. You should know these graphs, how to find their domain, their range. Are they even? Are they odd? Where do they increase? Where do they decrease? Usual questions that we ask. But furthermore, what we really wanted to know was, with these parent functions, if you memorize them, then you would know how to graph transformations, okay? So if you look at this, how would I figure out what this graph looks like? This is a transformation of f of x equal x squared, okay? So what has happened? So the negative in front tells me that it's been reflected about the x-axis, okay? And I know that that +1 inside the parentheses means that this has been shifted 1 to the right. And then that +2 on the end means that this has been shifted up 2 units, okay? So that's a transformation. So you'll need to know that sort of by looking algebraically and by looking at the graph, okay? Other things that we graphed polynomials, okay? This was a little bit complicated because it brought together several things. What is the degree of this polynomial? So if I look at this particular one, the degree of this thing is 4. That is an even degree. So I know this thing has to look like this. It has to look like x squared on the endpoints. The leading coefficient is 1, which is positive. So I can fill in the behavior, the limit notation behavior. X-intercepts, I get this straight by looking at the factors, 1, 0, -2, 0, and 3, 0. There's a multiplicity of 2 because of that exponent at x equal 3. I will not cross the axis when I go to graph this. And then to find the y-intercept, you set x equal to 0 in this equation, and you get 0, -18. So that will allow you to graph this. You graph the x-intercepts, okay? You know which places you cross, and you do the end behavior. So we'll do another example of this. That's just showing that for you. Other things we did graphically was, is a function even or odd? Okay, remember, if a function is even, it's symmetrical about the y-axis. That means it looks the same on both sides of the y-axis. If it's odd, it's symmetrical about the origin, or it looks opposite on both sides of the y-axis. So complete this graph, consider this graph to make it an even function. So if I wanted to make this an even function, I basically match everything 1 to 1. So coming over here at -7 right here, and at 5, so that makes this an even function, okay? These things should match. Now to make it an odd function, I basically do the opposite. So this point with the open circle, that's left 1 up 4. Opposite of left 1 up 4 is right 1 down 4. Okay, and then this the solid point is -7 up -7 up 4. The opposite of that is +7 down 4, which is right here. And then I also see this 0.5, so I see something like this. That makes this an odd function. Graphing the inverse of a function, okay? Remember the inverse, it interchanges the roles of x and y. So if you look at the point, this is where you just look at this, the hollow point there you see is that point 0,6. The inverse has to have the point 6, 0 on it, okay? So where is 6, 0? That is right here, okay? The solid point here is -6, 0. The inverse has to have the point 0, -6. So that is right here. And there was a line connecting those two. Then you look at the horizontal component there. That was 0,3. So if I've got a point 0,3, it's 3, 0 would be the inverse. And the point 4,3, the inverse is going to be at 3, 4, which is right here. So there is the inverse of that function. So you basically just switch the role of x and y. And that is what you see here where I graph the inverse. So you basically pick points and then you switch the role of x and y to graph them. Exponential functions, some of the last graphs that we did, they get a little bit complicated, but you should be able to pick 3 points and graph any of the exponential functions. So if I'm graphing 2 to the x, look at that exponent, and I want to figure out, let's set that exponent equal to 0, and then I want to pick one number on either side of that, and those 3 points will tell me what this graph is doing. So 2 to the 0 is 1, so 0, 1 is right here. 2 to the 1 is 2. 2 to the negative 1 is 1/2. I can see those 3 points, and I know immediately what this graph is doing, okay? This graph has a horizontal asymptote at the line y equals 0. As you can see, as I go to the left, I'm approaching that line, y equals 0. Now we should be able to graph translations of this function. So without going all the details of that, but let's just look and see. When I look at a function like this, that first negative in front tells me I'm reflected about the x-axis. The negative in the exponent tells me I'm reflected about the y-axis. That +1 tells me I'm moving to the left 1, and that -2 on the tail end tells me I move down 2, okay? So those are all the transformations that need to happen. So I've got my original graph, 2 to the x. That's the graph that you see right there. So just pick a point. There's a green point right here at 0, 1. Reflected about the x-axis, that takes me down here. Okay, reflected about the y-axis doesn't matter because I'm on the y-axis, okay? And then left 1 and down 2. Left 1, down 2, that puts me right here, okay? Now let's pick another color. Let's pick this point right here that's in red. Okay, reflected about the x-axis. Okay, if I reflected about the x-axis, it's 1/2, it goes to -1/2. Okay, that's right here. Reflected about the y-axis. Okay, go left 1 and down 2. That puts me right here. Okay, look at this open circle that you see here. Let's just go with green right here. Okay, reflected about the x-axis, that takes me down to here. Reflected about the y-axis, that takes me over to here. Go left 1 and down 2, and I'm right there, okay? So that's enough to tell me what the graph of this function looks like, okay? So let's do some graphs, okay? So this is based upon the parent function square root of x. I know that the square root of x normally looks like this. What has happened to this one? This one has moved to the left 1, okay? So the left 1 and down 2, okay? So I see that my graph is going to start right there and something like this. And this is what I see. That's the graph of f of x equal x plus square root of x plus 1 minus 2. The next graph, this is based upon x to the 2/3. I have to know that x to the 2/3 looks sort of like this. What has happened to it? The negative means it's been reflected. It hasn't been moved left or right, but it has moved up 3. So it starts here, and because it's reflected, my graph is going to do this. It's reflected about the x-axis. The next one is based upon the parent function x squared. We know that this is the parabola that looks like this. Okay, I've been reflected about the x-axis. I have moved 2 to the left and down 3. 2 to the left and down 3 puts me right here. If I reflect about the x-axis, then I see something that looks like this. X plus 4 cubed. Remember that x cubed is the graph that looks like this. So x plus 4 means I moved it 4 to the left. It's not moved up or down. So in this case, it's going to be like this. So that is x plus 4 cubed. Absolute value of x minus negative x minus 5 plus 1. Remember the absolute value of x, that's the one that just looks like the v. So what's happened? I've been reflected. I have moved 5 to the right and up 1. So 5 to the right and up 1, but reflected about the x-axis. That means my graph looks like this. X to the 1/3, that's the parent function that looks like this, okay? What has happened to mine? I have moved to the right one and up one. So to the right one and up one, and I have been reflected. So if I'm reflected, my general shape is going to be this way, okay? So if I look at that, I see a graph that looks like this. Now, you may be asked to give the domain and range of any of these guys just by reading the graph. Other things about graphing, you were given polynomials, okay? This is a polynomial that is what degree? So 3, 4, this is a 5th degree polynomial. That's an odd polynomial. The coefficient of this is going to be 1, which is a positive number. So odd positive means that this guy is going to look like this on the end behavior. It's going to look like x cubed does. Okay, what are the x-intercepts? 1, 0, 2, 0, and negative 3, 0. Is there multiplicity? Yes, there's a multiplicity of 2 at x equal negative 3. So I will not cross the axis at that point. What is the y-intercept? You get the y-intercept when you set x equal to 0. If you were to set x equal to 0 in this equation, you're going to get, let's see, what, 9 times 2, you're going to get 18. So 0, 18 is going to be the y-intercept of this polynomial. That's enough to graph this guy, okay? So at 0, 18, okay, that's my y-intercept. Now, my x-intercepts, I do not cross the axis at negative 3. So let's just do, so at negative 3, I do not cross the axis, okay? At 1, 0, I cross the axis, and at 2, 0, I cross the axis. I know that I start to the right, okay? So is it possible, let's see if I did this right. Okay, I started to graph this and I realized I made a mistake because the graph wasn't working out. What's the mistake that I made? There are a couple. So I didn't, this is not a 5th degree polynomial. This is 1, 2, 3, 4. This is a 4th degree polynomial. So that means that this is an even degree. Leading coefficient is the same, but that means the end behavior of this guy is it's going to go up on both ends, because when I tried to graph it the other way, it wasn't working out. So up on both ends means it comes here and bounces, goes up here, it crosses here, and then it has to cross here to go up to positive infinity. So that's the graph of this guy. Looking at the next one, this is a 3rd degree polynomial, which is odd. My leading coefficient is going to be -1, a negative number. So that means odd degree with a negative coefficient, that's going to look like negative x cubed. That's going to go up over here and down to the right. So x-intercepts are going to be at 2, 0, negative 2, 0, and 1, 0. There is no multiplicity. To find the y-intercept, set x equal to 0, and you get -2 times -2 is 4 with a negative sign, so 0, -4. So if I graph this at, so 0, -4, that's my y-intercept. I cross the axis at -2 and at 1 and 2, okay? So is it possible to do what I want? I can start up here, come down to the y-intercept, cross, and then end up in this area. So that's the general shape of this graph. Okay, how do I graph this guy? Okay, so it looks like I've got the intercepts. What, at -3, I will cross the graph, 1, 2, 3, cross the graph right here. I do not cross at 2, okay, so I do not cross there. If I look at this as a 3rd degree with a negative coefficient, it's going to look like this. And what is the y-intercept? You plug in x equal to 0 in this equation, and you get 3 times 4, so that's going to be a -12. So your x-intercept is going to be somewhere slightly off the graph here at -12. So is it possible to cross there, come back up, bounce, and end up? Yes. So the only thing this graph can do would be something like this. Graphing 3 to the x. Okay, this is where 3 points really all you need. Okay, so I want to pick 0 and a number on either side. So what is 3 to the 0? 3 to the 0 is 1. 3 to the 1 is 3. 3 to the negative 1 is 1 over 3 to the 1, which is 1/3. So I need to graph 0, 1, 1, 3, and negative 1, 1/3. So I see something that looks like this. Graph 3 to the x plus 2. Okay, so this is the same as 3 to the x, but it's just been moved, what, to the right 2. Okay, so I got two choices here. I can graph 3 to the x, which is what I just graphed a moment ago. So I graphed 3 to the x, which looked like this. Okay, so 3 to the x plus 2 is just moving this to the left by 2. So it would take every point and just move it over 2. Something like this. So this graph would look like this. Okay, so that's 3 to the x plus 2. 3 to the x plus 2 plus 1. Okay, that's the same graph that I had in purple, but it's moved up 1. So if you want to, I can say, okay, 3 to the x, I know what it looks like. Okay, that's what 3 to the x looks like. If I were to go left 2 and down 1, so take this point, go left 2, down 1, take this point, go left 2, down 1, the next point, left 2, down 1, and you see something that looks like this. And this one has a horizontal asymptote at the line y equal negative 1. That's where you get your horizontal asymptote from, that number right there. The next one, horizontal asymptote, is at y equal 2. So I can see that in the graph. So if I were to go to y equal 2, that's my horizontal asymptote. And it's basically the graph of 3 to the x that's been reflected, okay, and then moved up by 2. So what does 3 to the x look like? That's a 1 here, a 3 here. So it looks something like this. What would happen if I reflect it and move it up 2? So reflect it, moves it down here, 1, 2, moves it back to the same spot, okay. Reflect this, so it means down 3 and then move it up 2, which is right here, okay. And then here, if I reflect this and then move it up 2, so that's in this case, so something like this. And what you see is this behavior, which is the graph of the reflected negative 3 to the x plus 2. The next one's a little bit more complicated. So again, if I look at 3 to the x, so what does that one look like? That looks something like this. What has happened? So I need to account for that it's reflected about the x-axis. I need to reflect it about the y-axis. I need to move it to the left by 2, and I need to move it down by 2. So a lot of transformations that need to happen. So I take this point 0, 1, reflected about the x-axis. Okay, that comes down here. Reflected about the y-axis, it doesn't move. Go left 2 and down 2. Okay, so that is that point right there. So we've moved that one. Let's change colors. Let's take care of this point right here. Reflect it, that comes down 3. Okay, and then reflect it over the y-axis, that comes over here, and then go left 2 and down 2. Okay, that puts me right there. Take this point that you have at 1/3. So reflected about the y, reflected about the x, reflected about the y, and then go left 2 and down 2. So if I go left 2, so do that one again at 1/3. So I reflect it here about the x-axis, about the y-axis, then go left 2 and down 2. So something you see right here. about right here. And you can tell by this one, the horizontal asymptote is at -2. So I've got a horizontal asymptote right here. And so what this graph looks like is something like this. Complete to make the graph even, okay? To make the graph even, it needs to be symmetrical on both sides. So I got to have a matching point right here. And then I've got an open point here. And at 5, -4, I've got a closed point here. So I see this. That makes this an even graph. The next one, I want to make it odd. So odd means opposite. The dot that you see up there at -1, 5, -1, 5, the opposite of -1, 5 is 1, -5. So that's this point right here. The opposite of going to the left one is going to the right one. Okay. The opposite of going down 3 is going up 3. 1, 2, 3. So I get that. And then this -5, -4, the opposite of -5, -4 is 5, 4, which is right here. So that makes this an odd function. If the point -4, 7 is on a graph, what must be there if the graph is even? If the graph is even, I'm going to have 4, 7. When you take the opposite x value, you get the same y value. If it's an odd function, I need to see 4, -7 on that graph. If the point 7b is on the graph, if it's even, I need to see -7b. If it's odd, I need to see -7, -b. Continuing to graph, how would I draw the inverse? So the inverse of this function. Inverse means you change the role of x and y. So that point that is at, the point you see here at -1, 6, the inverse is going to be the point 6, -1. So at 6, -1 is right here. Okay. The point you see at -1, 0, the inverse is going to be 0, -1. So that's the point that you see right there. The point at 0, -3, the inverse of that is going to be -3, 0. So 1, 2, 3, 0, which is right there. And I can connect those dots. And then the point -5, -4, the inverse of that is going to be -4, -5. -4, -5 is right here. So there we go. That is the inverse that you see graphed. What's the domain of the original graph? Okay, the original graph, it looks like the domain is from -5 over to 0. What is the range of the original graph? The range of the original graph looks like it's from -4 up to 0. And then the other value that I get is 6. Okay. Now, what's the domain of the inverse? Okay, remember these just change role. I can look at the domain of the inverse looks like it's from -4 to 0 and includes the number 6. And the range of the inverse just looks like from -5 up to 0. Keeping in mind that there's a relationship. The domain of the original, these things should all match, okay? Domain and range, inverse, and the domain of the original is the range of the inverse. The range of the original is domain of the inverse. Graph a polynomial with certain properties. It has roots at 1, 3, and a double root at -1. So this has an x-intercept at 1, 0, at 3, 0, and at -1, 0. I'm told that there is a multiplicity of 2 at x equal -1. That means I do not cross the axis there. Graph the polynomial with a negative coefficient. So they're telling me it's a negative coefficient. If it has these roots, okay, this has to be an even degree because I've got 3 roots, but one of them occurs twice, okay? So this is an even degree polynomial. What would be its y-intercept? So I know that this function has to look like this. It has to be something times, what, x minus 1 times x minus 3 and x plus 1 squared. So f of 0 has to equal -1 Negative 3 times 1, which is 3. So 0, 3 is a y-intercept. So 1, 2, 3. So there's my y-intercept. X-intercepts. Okay, so I know I'm going to have them at 1, 2, 3, 1, 2, 3. I know at negative 1, I do not cross, but I do cross at 1 and 3. If this is an even degree with a negative coefficient, I know the end behavior has to look like this. Okay, so is it possible to do what I need to do there? Hold on just 1 second. And one minor thing here that I missed. This thing has I'm told it has a negative leading coefficient. There's got to be a negative in front of this. The minute I do this, this is 0, negative 3. So that was my mistake. So this should be at 0, negative 3. So 1, 2, 3. That's the y-intercept, okay? And so now I see the behavior of this graph. It starts up, it bounces right here. It picks up the y-intercept. It goes up and crosses, it crosses again, and there we are. That's all this graph can do. So I had a problem making that other y-intercept fit. It wasn't fitting my graph. I went back and realized I made a mistake. This thing I was told had a negative leading coefficient, so I had to take care of that. So that's a common mistake you may see. That's the end of graphing, guys. There was a lot to graphing. This is not everything. This is tip of the iceberg, but these were a good summary of the kinds of things that we graphed.